Hello and welcome on Risk Analysis course that is created by one young generation at Rovno Nuclear Power Plant. I am Alexey Koshkin, nuclear power plant operator and former PSA engineer, is going to make a short review on given subject. So there are a lot of fields nowadays where risk analysis, or call it better, safety assessment is used and applied, but on nuclear power plant it's of great importance.
Okay, let's finally begin our lesson. It covers fundamentals of risk assessment, so it's called 101. First of all, it's very useful to draw a distinction between risk and hazard. Any NPP, as any large facility, has a lot of hazards, but since proper safety procedures applied, the risk is at a minimum level. We distinguish two types of probabilistic risk assessment. It's qualitative and quantitative. Of course, detailed quantitative analysis of risk is always preferred, but in many cases this is neither practical nor possible. Qualitative assessment of risk, however, can always be performed and will usually take far less time and resources than quantitative. A qualitative risk assessment, or let's call it good industrial practices, should be a systematic examination of what in the workplace could cause harm to people or equipment, so the decisions can be made as to whether existing precautions or control measures are adequate. This is actually one of the areas where one works, sharing experience as well about accident as good practices, arranging visits of plant experts between power plants, etc. Of course, good industrial practices vary from industry to industry, but generally can be put in book like that one on the left. Usually those pocket guides contain list of hazards that should be taken into account before initiation of any procedures or checking workplace for potential threats. Some contain so-called checklists that should be read before starting any activity. For example, one on the right side is 2-minute job drill. Thanks for both to David from Monticello plant. Nevertheless, we mentioned semi-quantitative risk assessment that has a number of different techniques including risk matrices and lines of defense layers protection. As you understand, this is a hybrid of both methods. On the picture you can see matrix when we assess possibility and severity of some event, but in my opinion output of this definite matrix is not quite right, since we remember accident on Fukushima Daiichi in 2011 when series of events with really low possibility led to disaster. By the way, we have 10 years anniversary in 2021. Moreover, in the case of certain scenarios, the probability times consequence viewpoint would equate a low probability high damage scenario with a high probability low damage scenario. Clearly not the same thing at all. Still, more guys are rather interested in quantitative methods, maybe because thinking of Monte Carlo generator sends our imagination to the Europe's gambling capital. By the way, this technique was first used by scientists working on a bomb. Those different distributions I inserted here is about to show that risk assessment process can be quite ambiguous and that this is not a lead pipe cinch. As we said, quantitative risk assessment requires experts to do analysis, using comprehensive databases compiled from years of industry operation. As a result, we focus more attention on this part. But before jumping in science, we have to answer three simple questions. What can happen? How likely is that will happen? And if it does, what are the consequences? Of course, these are not all features needed to conduct real-life safety assessment, but I hope that's enough for our class. Depending on what we are assessing, outputs may include level 1, level 2 or level 3. Okay, for now we're using the method of small event trees with big fault trees attached to its node. Suppose we have primary circuit leakage. At first we have initiate an event Then series of mitigating functions designed to return our system to safe operation and avoid major damage. In case of design basis accident, of course. In our example, we have some safety systems that respond or fail to respond with some frequency to certain event. When arrow goes up, it's success, opposite, fail. With red color punctured code damage sequence. Good. For now, let's solve some easy problem. For instance, I get to my job by company bus that sometimes changed its route due to roadworks. Plant management informs its employees in advance, but people tend to forget information, moreover, some even haven't heard of it. What is the possibility of being late? Okay, the initial event here is roadworks that takes 10 days per year, for instance. Here we also consider external events like bus and driver state. Moreover, we have safety function as coworker who goes by car. Where did I get those probabilities? Frankly, I didn't do any data mining, but I've just assigned them, and let's put a pin in it for now. Since we are familiar with the event, let's take a look at fault tree. Here we have example of high pressure injection system, and we'll try find out causes and elements itself that will fail the system function. Okay, here we have basic elements like valves, tanks and pumps. Of course, it's simplified scheme and we omit some elements as electric supply, service water, etc. All of that can be put in the box of dependent failures or common cause failures. One pump, but we distinguish fail to start and fail to run, since the different initiators behind these fails. We also consider tanks, since they can be clogged, suction tank, or just empty after maintenance. Also, we have requirements for valves to be in certain position, recirculation, closed, suction and discharge open. Solution of fault tree is called a cassette equation. Applying probabilities we calculate when system is unavailable. And question for you, can we use fault trees without data on frequencies? Answer is yes. It's still great to generate cassettes, and we already done it. Our cassette is below. You see in case of AND gate we multiply inputs, and for OR gate failure of any input causes overall fail. But what probability should we assign for calculation? It's okay when we have some history, but quite often they are known, especially for rare events. I think this topic is pretty good discussed by Kaplan and Garrick back in 1980. In general, statistics is the science of handling data. On the other hand, probability as a subject, we might say, is the science of handling the lack of data. Usually we have few sources of data. Those events happened on our plant, on different plants of the same design, and even different industries. But how to combine these types of information? Bayes' theorem serves this purpose. Let's look at example. For instance, we have general failure rates, and we should adapt them for our case, for NPP or unit. Here, Bayes' theorem is employed for updating generic data. Generic data refers to the parameter related information that is non-specific to any particular plant or application, being an aggregation over more than one data source. And sources on the screen. But how to combine obtained numbers with real life? This table helps you. Finally, with development of computational methods, a lot of industries, not only nuclear, started to use risk assessment. But numbers sometimes can fool you. This example demonstrated. In 1997, the US Weather Service forecast that North Dakota rising Red River would crest at 49 feet. Officials in Great Forks made flood management plans based on this single figure, which represented an average. In fact, the river crested above 50 feet, breaching the dikes and unleashing a flood that forced 50,000 people from their homes. It's only one single example of misuse of data. Have to remind you that this was my first experience with video lectures. Write your feedback and I'll improve this draft. Thank you very much.